Hello everyone, welcome to another video on quantum mechanics. In today's video, I'll be talking about the radial wave equation in quantum mechanics. Now, in case you guys didn't know, this is actually a continuation of a series titled the hydrogen atom, where we actually build up to solving the wave function for the hydrogen atom. Now, in my last two videos, I went over how to derive the spherical harmonics and how to solve for some of them and check their orthonormality. So in this video, I'll be talking about the radial equation and how it's actually important in solving the wave function for the hydrogen atom. So without any more further ado, let us begin. So let's just do some review over here. If you recall from the first video in this series, the wave function is a function of the radius, the angle theta, and an angle phi. This is a wave function in the 3D spherical coordinate space. And we assume that the wave function is separable into a radial part and an angular part. Now this angular part, we call that the spherical harmonics. And the previous two videos focused on just that. But we also learned that the spherical harmonics are actually dormant. If our potential is radial, which for the atom it is, our spherical harmonics aren't going to change depending on, the spherical harmonics won't change depending on the radius, since the potential is purely radial. The spherical harmonics won't depend on the potential, since the potential is purely radial. And since it's the potential that changes the wave function, the spherical harmonics isn't going to change. So what does actually change is this part. We call this the radial wave function. And it's this that the potential depends on. Now, of course, we could construct a theory where the potential depends on the angular terms, but that theory wouldn't just describe actual atoms as we know them. So we work with radial dependent potentials. So if you can also recall from the first video, we actually derived a relation. We derived this over here. I'll talk about what it means in a short moment. So V of R minus E, R equals L times L plus 1 R. So we actually derived this equation in the first video. Now again, if this seems pretty wishy-washy or odd to you guys, I recommend watching the previous two videos in this series. Again, this series is titled the hydrogen atom. Now we derived this equation. We actually derived them when showing how the radial function and the angular function depend on different variables, yet actually equaled a constant when subtracted from each other, and that implied that both parts are equal to constant, and through some more logic, we derived this equation. So, if you guys don't know where this comes from, watch the first video. But yeah, we have this equation over here. We actually multiply both sides by R to the right, so this exact equation. And then this is almost the radial equation. So, in principle, we can actually solve this equation for R of R. But we can make some more, we can modify it a tad bit to make our lives a bit easier. So we actually put a change of variables. Let's make a change of variables here. Let's let U of R be defined as R, small r, the radius, times R, big R, the radial function, R of R. So making this substitution, this implies that big R equals U over little r. It implies that dr over d little r equals r times du over dr minus u over r squared. Also implies that d over dr of r squared dr over dr. Look, that's actually this part over here. plus this equals RD squared U over dr. And you can check all of these yourselves from this definition of U over here. So what we can do now is we can substitute this part for this over here in the other parts, and then do some rearranging, and you actually arrive at this equation. Minus h bar squared over 2m, second derivative of u with respect to r, plus v of r, plus h bar squared over 2m, l times l plus 1, over r squared times u equals EU. So again, all we used here was changing variables and moving the equation around a bit, and we arrive at this equation. And this is what we call the radial wave equation. And this is the equation that we actually care about, since it is this equation that we solve for, well, really, we solve for u of r, and from u of r, we can just divide that by r to actually obtain our radial wave function. And it's this radial wave function that we care about, since it's the only thing that can freely change depending on our potential. So when we solve for the wave function for a hydrogen atom, what we're really solving, well, what we will literally solve is the radial wave function for the hydrogen atom. And we actually input the hydrogen atom potential into v of r. And from this radial wave equation, we will find big R of r, and then we just stack on that spherical harmonic term to get the total wave function. But it is this that we actually care about, since it's what depends on our potential. So this is our radial wave function. Now let's just talk about the structure of this function. Now you may notice it sort of resembles the time independent Schrodinger equation for one dimension. I'm going to write that down over here. So second derivative of psi with respect to x plus v psi equals e psi. This closely resembles this because it has one dimension here, the radius, and well, we have e psi, eu, we have these match up. It's only this part in this term that doesn't actually match up, isn't actually in isomorphism, well, not isomorphism, isn't actually injective with this position dependent equation here. So if we treat this part as like one big new potential, then this equation will be like 1-to-1 with this equation over here, but this part will sort of throws us off. And it turns out that it's this part, this term over here, that's going to make us solving for the orbitals of the hydrogen atom quite difficult to do, and solving for orbitals in the general case very hard to do, since this part is going to mess up our differential equations, and we'll see that in a moment. So we can treat this whole thing as some new potential called the effective potential. And the effective potential is going to be v of r plus h bar squared over 2m. Now, note that this isn't actually the potential energy. This is the potential energy, but it's kind of like this entire thing is the potential energy, so that it would map 1-to-1 with the one-dimensional position case for the Schrodinger equation. So this is what we call the effective potential. And what is the physical meaning of this term? Well, this term is actually what's called a centrifugal term. It sort of acts like the centrifugal force that we know from classical mechanics. So what it does is that we have the proton. This is like when we solve the hydrogen atom. You have the proton over here. You have the electron. The electron moving around the proton. And this term over here is going to tend to kind of throw the electron off its natural orbit, kind of move away. So it's like how if you're in a merry-go-round or spinning, you feel a force like pulling you back, and this is what this term does. It tends to fling out particles like away. Now for actual atoms, it isn't going to be that extreme, but that's what it kind of does. It kind of pulls the particles backwards. So that's where the name comes from. And then this is the effective potential, since it's effectively acting as a potential. Okay, so that's the radial wave equation. Now let's actually solve this equation for some potential. So, say we have the potential V of r. Again, it can't have theta or phi in here. And let's define this potential, like this scenario, as being 0. The potential is 0 if r is greater than or equal to some number a. And it's infinity if r is greater than a, where r is the radius here. So let's actually graph this before we actually solve this. So here we have z-axis, x-axis, the y-axis, and then here we have some radius r, we have some angle phi, and then here, like r, this would go down, and then we'd have some angle theta, yes, some angle theta. All right, and theta, r and phi constitutes our spherical coordinate system. So what this actually says is that our potential is 0 if x is greater than some radius a. Okay, so say that a is this over here. Here's a. It means that for all radiuses greater than a, so radiuses longer than a, our potential goes to infinity. But less than a, our potential is going to be 0. It's going to be free. And note that the radius goes around this entire coordinate system, right? So it actually forms a sphere. It actually forms a sphere that looks something like this. Remember, because we have a radius here, and the radius like traces out a sphere in three-dimensional space. So inside of the sphere, we have a radius less than that of a. But outside of the sphere, we have a radius greater than a. So inside of this sphere, our potential is going to be 0, outside infinity. Now recall from like the infinite square well, a particle cannot exist in an area where there is an infinite potential, since that requires an infinite amount of work, right? So the wave function is going to be 0 outside and non-zero inside. All right. This is actually very analogous to what we did in my video called N-fold degeneracy of a particle in a 3D box. In fact, it's almost exact, because in that video, I solved the Schrödinger equation for a infinite square cube well. And here, we're solving it for an infinite cube. Sorry, let me just try to reword that. In that video, it's titled N-fold degeneracy in quantum mechanics, we solve the Schrödinger equation for a potential that was actually in the shape of a cube. So let me draw that right now. We have z, we have x, here have y, and our potential was actually in the shape of a cube. And inside the cube below 0, outside infinity, and here we have almost the same thing. Inside the sphere, it's 0, outside, it's infinity. So here, we call this the infinite cube, like cubular, I think, well. And here's the, not cubular, infinite spherical well. I forgot my shapes for a moment. And this is what's called the infinite cubular well. And then we have the infinite square well for the one-dimensional case. And for the infinite cubular well, we have v of x, y, z. It's like 0 if like ax is less than x and stuff, like the analogous thing. So I really recommend watching that video. The title is N-fold degeneracy in quantum mechanics, because we just solved for a similar thing, but just in Cartesian coordinates. But here instead we have spherical coordinates. And this is what our potential looks like. It's 0 here, outside it's going to be like infinity, diverges and stuff. Okay, so let's actually solve this equation. Enough like jibber jabber. So let's solve this. Alright. Okay. So, of course, the wave function is only non-zero inside of this inside this sphere. So let's actually solve the equation for inside the sphere, and of course outside it's going to be trivially 0. So for for r is less than or equal to a, we have that. Well, let's actually just write out our radial wave equation again. The radial wave equation is going to be minus h bar squared over 2m times this v of r plus h bar squared over 2m l times l plus 1 for r squared u equals eu. Alright? Now for r is less than or equal to a, we have minus h bar squared over 2m u for dr squared plus h bar squared over 2m l times l plus 1 over r squared u, should be u here, right? Yeah, u equals eu. Okay, this is because the potential is 0 inside of that sphere. Now, you guys can probably see why this part here, messes up our equation. Because if this was actually 0, if the effective potential was 0, we just have a free particle equation. But it's not 0. And that messes things up. So, let's actually consider the case where L is 0. Now, when L is 0, this whole term actually does go to 0. And you have minus h bar squared over 2m, some derivative of u, with respect to r, equals eu. And this is just the free particle wave equation. So we have u of r is going to be let's actually write in terms of sinusoids. It's going to be a sine of kr plus b cosine of kr. We're going to write a and b in terms of imaginary numbers. Okay, so note, this is for the case where L equals 0. Note here that k is being defined as the square root of 2me over h bar. And what do we have to do now? Well, here's u of r, right? Remember that u is going to be r, big R over small r. So r of r is going to be a sine of kr over r plus b cosine of kr over r, right? Now, what happens as r approaches 0? Well, as r approaches 0, this term over here diverges due to the cosine of kr term here. So we have to make b equal to 0 for the radial wave function to be normalized. So letting b equal 0, we now have a u of r equals a sine of kr. So technically speaking, this isn't a fully proper argument, since we actually can let r approach 0. Like, it is true that u of r, well, r of r is going to approach infinity as r approaches 0, right? It is going to approach infinity. But we can still have a function approach infinity from the right-hand side and still be normalized, right? So we have to form a better argument, and yeah, this argument that we use isn't perfect, but it's good enough that we can continue this video. So it has some problems, but it's good enough for now. So u of r is going to be a sine of kr. Great. Okay, let me just move this up a little bit. So u of r is a sine of kr. Now what do we do? Well, now we have to impose some boundary conditions. So we have to impose the boundary condition that, what boundary condition are we imposing? Wait. You have to impose the condition where u of a equals 0, right? Since our potential is going to be infinity if r equals a. So u of a has to be 0. This, of course, implies that a sine of ka equals 0, which implies that k equals n pi over, is it r, I think? K equals n pi over a. So k equals n pi over a, and that will let this hold. Since remember that, sorry, wait, let me just think of it. I think I'm losing track. Okay, so we have Ka equals 0, right? Yeah. So this implies that Ka equals n pi, since sine of n pi is 0. And this implies that K equals n pi over A. Okay, there we go. Trying to make sure that was right there. So K equals n pi over A. And remember that K is also the square root of 2me over h bar. So this actually implies that E equals n squared pi squared h bar squared over 2ma squared. Alright, just checking my notes to see if I have everything correct. Yes. Okay, so this is going to be, well, yeah, our energy eigenvalues, and it depends on this thing called n, also known as the principal quantum number. Okay, great. But we still have a slight problem. Oh, wait. So also we have to normalize u of a. Doing normalization, we find that a equals the square root of 2 over small a. So this is actually all fine and dandy. But the problem is this is only for L equals 0. If L is not 0, in the most general case, this part, this term over here, this centrifugal term is non-zero. We have a problem. We can't write u of r in terms of plane waves. Well, these weren't plane waves, these are sinusoids. We can't write it in terms of sinusoids anymore. We can't solve the differential equation in that way. So instead, we have to use a different technique for solving differential equations. So for L it's not 0. Well, let me try this step. So for L does equal 0, but that u of r is square root of 2 over a sine of n pi over a r. Okay. That's u of r. But what about for L is not equal to 0? Well, for L is not equal to 0, our Schrödinger equation is square root of h bar squared to m, this over this, plus h bar squared over 2m, L times L plus 1 over r squared u equals EU. Well, it's actually a very clever trick that we can actually employ to solve this differential equation. It's a trick that isn't very well known, but it's very, very powerful. So to solve this equation, what we can do is we can actually plug this into Mathematica. And doing that will give us the solution to our differential equation. Very clever, right? And our solution, it's a very powerful trick for differentiation. They just say integration for differentiation. And the solution that we get is, let me just find my notes, is u of r equals ARJL KR plus BRNL KR. That's our general equation, where JL are the Bessel functions defined as minus x to the L of 1 over x d over dx to the L sine of x over x, and NLX is minus x to the L 1 over x d over dx to the L cosine of x, cosine of x over x. Okay, so you guys might be confused, and you will rightly be confused. So what are we doing here? How do we even get this thing? So to answer the equation, how do we actually get this part? Yes, we have to plug it into Mathematica. And there is a way to actually solve this explicitly. And we will not do that because we don't want to waste our time. We can just plug this thing into Mathematica. No need for any brute force here. And these things are called, this is called the Bessel function. This is called the, what's it called again? Let me check my notes. This is called the Newman function. The Bessel function is defined as this. The Newman function is defined as this over here. So all this is saying is that u of r equals AR times this whole thing over here of KR. So you have to plug in KR for x, really? Plus BRNL of KR. So you have to plug in KR here for x again. And that's actually the general solution to an equation that looks like this. And again, here, I believe, I'm not too sure, but I believe that k is still defined as square root of 2me over h bar. So this is the general solution, and our energies to this solution is E, and now it depends on L. Actually, here I said En was this. This should be En0 for L equals 0. You have En is going to be, let me check my notes, it's h bar squared over 2ma squared times this b squared and L. You guys may ask, what is this b term? And I actually forgot what this b term is. Sorry about that. You can just look it up, but I'm not really sure where it is. So this is E and L. This b and L term is going to be like another function, I believe. Not too sure though. I'll write it down in the comments after I find it out. But yeah, these are our eigenvalues, and this is our eigenfunction for the general case of L. Okay, so we're pretty much done here. So this implies the R of R. Again, technically B goes to 0 here. So R of R is going to be A N L J L times B and L R over A. That's going to be big R of R. So psi of R, beta, and phi is going to be this exact same thing times the spherical harmonics. And then we can take the squared value of those to get our orbitals for this system. But we don't really care about that right now. We don't really care about this either. We care about the radial wave function. So yeah, that almost done here. We have to talk about normalization. So when we normalize our wave function in spherical coordinates, it looks like this. The r d theta d phi. We break this up into r and y to get this. Where here we define the omega as sine theta d phi. Okay? So if this is normalized, this has to be equal to 1, which implies that both of these have to be 1, right? So this implies that the integral of this should be 1. And let's again use u equals r, small r, big R, implying that this is just going to be u squared. So u squared dr is 1. This is our normalization condition for u of r. And of course, this is from 0 to r. Sorry, from 0 to infinity, since our radius is only going to be non-negative. Alright, so that actually concludes this video on the radial equation. I hope that you guys enjoyed that video. And in our next video, I will be solving we'll be finally solving the Schrödinger equation of the hydrogen atom. And that's going to be pretty fun. So have a great day, stay safe, and see you guys next time. Bye.